when you have two teeth in contact, you see force being generated, and that is how you generate torque or motion to it. So with that said, what would we do in ANSYS? So we would simulate all these gears. So on the slide here is what you see for a spur gear assembly. So you would have a driver, and you have and the other gear is driven by it. So you give angular motion to it, all the steps to it. One important thing, as I said, the base circle and the pitch circle it's so important when you come across gear design. So uh, as you do this, we'll be simulating something like this. And another one I had here was a bevel gear assembly. So where you will be simulating, will be running simulations for bevel gear and see how long does it take for it to fail. So when you look at spur gear and bevel gear, it's gonna do the same thing, right? So when you take this bevel gear, it's gonna be in contact with another one teeth, and it keeps rotating. But do you think the part is gonna fail or not? The answer is yes, it's gonna fail at one point. So what is that? Why does it get failed? And the reason for it is yes, fatigue. So fatigue is nothing but failure due to repeated cycle. So when you have any gear assembly, all these steps, your part is definitely gonna fail at one point, right? So if it keeps repeating, and at one point your part is gonna fail, and that is what fatigue here is. The types of stress which is developed are the axial bending, twisting stress on your part. So fatigue, how does it work? So it's the same like what we were talking initially. So it's gonna have some crack being developed, it propagates, and it's gonna fail at one point. And the reason for it is because of fatigue, which is failure due to repeated loading. So when you talk about fatigue, there is one important step which come across, which is the ascent curve, which is which is to do with the amplitude and number of cycles to failure. So they generally run a test, give some repeated loading, give some specific load, see how long does it take for it to fail. So that is what down here. So yes, here represents the amplitude, the stress amplitude. N represents the number of cycles to failure. So for so they have come up with this ascent curve for most of the materials. So I believe you would have come across this. So this is showing the stress strain plot, stress amplitude, which is on the y-axis, and x-axis is the number of cycles it takes to fail. So there is one limit called the fatigue limit. So fatigue limit is, what does it actually mean? Let's say if the stress applied is lesser than this fatigue limit, your part is gonna live long enough the whole life. So that is what this plot represents. I just had a quick SN plot showing you difference between a steel and aluminum. So looking at the plot again, here is you have stress on the y-axis and number of cycles on the x-axis. So what does it say here? So when you look at, let's say the load we apply is 90 ksi. So we apply, let's take this spur gear. Okay, so we apply this specific load, keep on repeating. This is the load your gear is going to take. So when would the gear fail? The SN plot is actually used to determine when it would fail. So for a load of 90 ksi or 90 psi, your part is going to fail at 100,000 fatigue life. So this is the point. So 10 power 5 is the number of cycle it would take, after which your part is going to fail. So this is how they come up with a life of gears and steps. So when you look at steel, you see that there is some, it keeps as the load keeps decreasing, you see that it keeps decreasing, and at one point it flattens out. So for steel, there's a fatigue limit, so which is shown as 60,000 psi, but whereas for aluminum, magnesium, copper, there's no fatigue limit. It's just like if you know the load it takes, and you can determine number of cycle it takes to fail. So this one step which I just wanted to give you an overview on. We'll moving. The other one, coming to ANSYS part, uh, we have seen bolt nut washer assembly all our life. So you have in this case right now we are seeing only the bolt and the washer. So you generally just take a bolt, you just torque it, tighten it, and just finish it up. But what does it actually take? So here is a simulation of bolt nut washer assembly. You have this bolt. You are trying to simulate a torquing to it, and as you torque it, you see the washer gets deformed and gets in contact with the bolt. So this is showing you the cross section and the simulation of it. So you can just look at the washer as you as you torque it, the washer gets deformed and it gets flattened out. So that is this is the type of nonlinear analysis we do in ANSYS. You have this option of doing a section to look specifically where you want to look, and the other one is just looking at one specific part. Right now you're seeing only the washer. As you torque it, you could see the deformation it takes. In this case, it's showing the stress developed as you torque it. So that's one option you have. You can keep looking at each of the parts separately. So this is a simulation showing like once it gets in contact, this is just showing you the bolt. As the washer gets contact to each other to the bolt, you're just seeing the simulation. So just seeing how what's the strain developed as the washer is being crushed. Okay, so that's one thing we would do in ANSYS. With all these said, when you have this bolt nut assembly, anything you would have come across this term friction. So friction is nothing but the force to oppose the motion of an object. Uh, you have two different types. One is like just rotatory, which is something to do with rolling. So when you push a wheel, the wheel rolls forward, and there's been friction resist due to rolling. And an other example I have is like pushing a box. So force you apply and a friction being developed. As I mentioned, friction is nothing but force that opposes the motion of an object. So it is actually given by this formula. Static friction force is nothing but a function of normal force, but it is actually given by a coefficient called coefficient of static friction. So with that said, I had another picture showing you what different types of motion we have. One would be sliding, the other one would be rolling. So what do you think is the unit of coefficient of friction? So so which is down here. So we were saying that frictional force is nothing but a function of normal force, and which is given by coefficient. Yes, so it has no units. The reason being because this friction force, the unit is Newton, and the normal force is Newton, so it gets cancelled out, and that's the reason why you don't have a unit for coefficient of friction. So always remember this. So whenever you like do some calculations by mistake, you always tend to put some unit to it. So it is definitely dimensionless. Just try to cross off based on what equation you have to determine whether or not your function is unitless or not. Okay.